Hey guys, how's everything going? Let's continue our journey of LeetCode. Today it's about 1123, lowest common ancestor of deepest leaves. Wow, it looks hard. Given a rooted binary tree, return the lowest common ancestor of its deepest leaves. Recall that the node of a binary tree is a leaf, and only if has its no children. Yeah, the depth of the root of the tree is 0. And if the depth of another node is d, the depth of each of its subtree is d plus 1. Of course, the lowest common ancestor of a set S of nodes is node A, with the largest depth such as every node in S is subtree with root A. S nodes in a node A with the largest depth such that every node in S is a subtree node. No, what? The lowest common ancestor of a set S of nodes is a set of S of nodes in the node A. Okay? With the largest depth such that every node in an S is a subtree with a root A. Well, I don't know what he's saying. The lowest common ancestor of a set S of nodes is the node A, okay? With the largest depths, okay, such that every node in S is in the subtree with the root of A. Well, I couldn't understand this part. The lowest common ancestor of a set S. I got. So for a set of nodes, the lowest common ancestor means is a node A with the largest steps. Okay, so that every node in S in the subroot with A. Wow. Okay, now I understand it. Okay, for like we're given a root of, let's analyze it. 1, 2, 3. The deepest leaves would be 2 and 3 because they are different. So the roots must be 1. So return 1. Oh, right. Like 1, 2, 3, 4. So the deepest only be 4, and the child would be 4 itself, the common ancestor, because there's no other thing, just itself. Right. Okay, 1, 2, 3, 4, 5. The deepest would be 4 and 5. And the 2, so the common would be 2. Right? So 2, 4, 5. Yeah, cool. So actually we have, after we examine 2 examples, we have deducted some characteristic of this problem. The first one is for a parent node like 2, 4, 5. 2 would only be one of the possibilities of the common ancestor if the height of left and right are the same. So for this case, 2 might be the answer, right? But if it's not, then 2 cannot be the common ancestor because there's nothing to be common. 4 is enough. Right, so for this case, and if we think of this 4 have two child of null, then of course the height of left and right is the same as 0, right? So 4 is the possible common ancestor. Well, this reminds us of a solution which was based on recursion. The problem is, for a node, it could only be possible as ancestor if left and right has the same height. And we recurse it. We do the recursion, go to left and go to top, to bottom, we can just return the height of each tree, right? If we return that, it could be a possible. We can determine if we can determine if it is a possible common ancestor or not. But there's a problem that for this case, like 4 is possible, and 3 is also possible. Let's put a simple way, like 5. 4 is possible, 5 is possible, and 2. 2 is also possible. But 2 is higher, right? So 2 is absolutely the possible, the better option for 4 than 4 and 5. But there's a problem that we met 3. How would handle that? Like there's a 4 here. 4 is a candidate, and 3 is a candidate. But 3 will be processed after 4. Right? So, but we need to pick 4 because 4 has deepest tree than 3, right? So that means that we need to calculate what's the depth of the deepest one. Like there's 5 like this, then 5 is possible, and 3 is possible. And if this like this, 5 is possible, 6 is possible, and a 4 is possible, but 4 has equal length. For the deepest leaf node from 4 is 5 or 6. It's equal to 5 and 6 itself, but 4 is processed later than that, so it's higher than 5 and 4, so it's a better option. And now 3, like 3, there is like 7 and 8. Like we made 7, the depth of the longest, the deepest leaf node would be 3, right? So it's comparing it to 6. It's shorter, so we won't update the maximum. So update the candidate. So for each node, not we only get the height of the subtree, left subtree, right subtree, we also need to consider the depths from the root. Like for 4, there is 1, it's 0. Oh, okay, so here it says 0, and there is 1, 2, 3. Now for 4, the depths from above is 2, the depths from below is 1. So the subtree which pass through 4, the maximum of the depth would be 3. For 7, below it 0, to it 2. So sum, it's 2. So it's smaller than 3 here. So comparing 4, it is not that good on a candidate, right? Cool. So we can start our famous walk method. The parameter is simple. It's a node. But what we return? We return the height, which means depths. Means how many layers of node the tree has. Okay, so when the walk is ready, I say for a walk how we handle it. Of course, if node is null, just return 0, right? For the null here, nothing. There's nothing. So now we say left height. We now get left height and the right height. What we do? Okay, if left equals right height, it is possible candidate, right? Left is right. It's a common ancestor. Now of course, we need to track const let result equals. We need to compare the maximum the maximum height. So we use two. We use two elements. The first one is height of leaf node, and then node itself would be, and this would be 0 root. So when it's same, we need to I'm sorry. We need to get the receive the depths from above also. We need to pass down the depths also. Depth. So now we need to compare if compare the depths of leaf node. Wow, the depths of leaf node would be depths, which is passed. So this index here plus left count, right? Left and right. So would be plus left height. Let's say for 4, it will be passed. Okay, I'm sorry. This should be plus depths plus 1. Depths plus 1. So now we say we got 1. For root we get depths 0. Now we get 4. We get 2. And 5. With 5 we return 5. We go to left node. It's null. We turn 0. So for 5 itself, the depths would be depths of leaf node would be the 5 will be passed with 3. So the depths leaf node of would be depths plus left height. Left height, it will be 0 and plus itself. When we go to 4, we traverse with here is 0. Go to 4 with 1. Go to 4 with 2. Go to 5 with 3. Left one is 0. Right is 0. So depths would be 1, 2, 3, 4. Would be okay. I think this will be good. And if it's bigger than it, bigger than results 0 or equal to is okay. Result would be updated, right? And the result 1 would be node. So we update it. Now we need to return the height. So the height would be simple. We return the math max biggest one on the left height or right height. But we need to plus 1 for itself, right? For 5, the left will be 0, right will be 0, but itself will be 1. Okay, I think we're done. So finally we return the result 1. Cool. Let's submit. Wow, wrong answer. What? 1, 2, 3, 4. We got the wrong answer. Why? Okay, 1, 2, 3, 4. Let's see if I can debug it. Okay, we walked 1, 2, 4. 4 is possible. So, and the depth would be 2. So we update it. Console log. Hmm? Console log. Ah, we didn't walk? Oh, fuck. Sorry, I forgot to walk. Root. Hmm? Still, there's mistake. Console log. Node root. Whoops. Let's say the val. So we traverse to 4. Uh-huh. The result would be 0, 0, and root. Hmm? That's absurd. Okay, left, right, with steps. Ooh, depths. Ah, God. Oh, shit. Cool. My bad. Wow. Wow. I never once have made it to write a bug-free code. Submit. Cool. We're accepted. Now let's analyze the time and space complexity. For time, each node will be it travels only once, so it's obviously n, the count of nodes. Space, we use this array to keep track of the maximum. And there's a call stack. Maximum would be the n worst call stack. Okay, so that's all for this problem. Hope it helps. Is there a way to do it in I should say, is there a way to do it in a iteration way? I don't think so because we need to get the parent. If we do it iteratively, like one, we know we could know we could well of course we could maybe possible we could just do it DFS, right? When one we we could do it like go straight away. When we process one, we stack to 2 and then stack 4. Well, I think this is good enough, so I'll stop here. I hope it helps. See you next time.